1 over 2.2 times 10 to the 6. Well, this is carbon monoxide, difluoride, carbon dioxide. Okay. Well, this is carbon monoxide, difluoride. Okay, that's okay. So now I've got it flipped. Now I have a lineup of the same compounds on the same side. But if I compare this reaction to this reaction, this one is a square of this one. So if I want to go to 2 carbon dioxides plus 2 carbon tetrafluorides to 4 carbon monoxide difluorides, then the equilibrium constant here is just going to be 1 over 2.2 times 10 to the 6 squared. Okay? You guys can punch it through your calculator. I've got it set up for you. I would also suggest that you look at more practice problem 15.2 because you got to figure out how to add 2 reactions together to get the third reaction. Okay? So those are all things that I expect you to be able to do. You just fell. Sorry, guys. You have been retrieved. Okay, let's make sure that everything's lined up correctly. All right, we're good. Okay, last point. When a pure material, a solid or a liquid, appears in a reaction, so you see as the subscript S or L, its concentration isn't going to change over the course of the chemical reaction. Therefore, those concentrations are considered to be lumped in with the equilibrium constant, and they do not appear in the equilibrium expression. So when you have a solid or a liquid in a reaction, they're not going to appear in the equilibrium expression. So let me show you a couple examples of what I mean. Okay? So if I take carbon dioxide gas and we decompose it into carbon solid and oxygen gas, the equilibrium expression is going to be the concentration of oxygen over the concentration of carbon dioxide. The carbon doesn't appear because it's a solid. Okay? Another example that we're going to run into quite a bit is a reaction like the following. If I have HCl aqueous and I react it with water liquid, I get H3O plus aqueous and Cl minus aqueous. If I write the equilibrium expression for this, we have H3O plus times Cl minus all over HCl concentration. The water doesn't appear because it's a liquid. Because pure water has a concentration of 55 molar. Even with this reaction, there's not enough change in the concentration of water to be noticeable. So it doesn't appear in the equilibrium expression. Okay, roll up. Okay guys, I've put a handy dandy table here in the notes for you. It's got all of the things we just talked about. If you reverse a reaction, you invert. If you add 2 reactions together, you multiply. If you multiply the reaction by a coefficient n, you raise the equilibrium expression to k, and solids and liquids are not included. So everything's there for you in a handy table. Okay? Now, before we leave this alone, we're going to look at problem 15.4. Just one more example. 15.4, 561. Oh, don't have to worry about that. We've already done an example. Now, most reactions we deal with happen in an aqueous environment. But some chemical reactions happen in the gaseous state. Remember, we talked about chemical reactions happening and how some of the particles at least have to be moving. So the liquid phase, something being aqueous, dissolved up in a liquid like water, or in the gaseous phase is where we're going to see chemical reactions happen. So in some cases where the reactants are gases, there are two ways to express concentration. Okay? The two ways to express concentration are pressure and molarity. Now remember, molarity is moles of solute divided by volume of solution in liters, and pressure, PV equals nRT, partial pressure, reminder, is the pressure exerted by one specific kind of gas molecule in a chamber. It's the portion of the overall pressure in the chamber exerted by that one type of gas particle, partial pressure. Now, looking at this, scroll up a little bit. Yeah. Pressure, if I divide through by the volume and get pressure by itself, I get N divided by V times RT. I should have put some parentheses there. N divided by V is molarity. So pressure equals molarity times R times T, which means there's a relationship between partial pressure and the concentration of the gases. Namely, the higher the concentration, the higher the partial pressure is going to be. So this gives us a second way to express equilibrium constants. We can talk about equilibrium constants in terms of concentration, or if we have gaseous reactions, we can express it in terms of partial pressures, Kp. And there's a relationship between the two. Now let me come over here and write some stuff for you. So if I had the reaction carbon monoxide, two carbon monoxides in the gas phase reacting with oxygen in the gas phase to give me two carbon dioxides in the gas phase, I could write Kc for this, which would be the concentration of carbon dioxide squared over the concentration of carbon monoxide squared times the concentration of oxygen. That's Kc. Kp would look like this: the partial pressure of carbon dioxide squared over the partial pressure of carbon monoxide squared times the partial pressure of oxygen. Okay, so if you see, this is in terms of concentration, this is in terms of partial pressure. Now, there is a relationship between Kp and Kc. Namely, the equilibrium constant in terms of pressure is equal to the equilibrium constant in terms of concentration times RT to the delta N. Now, delta N, N always represents moles for us. And in this case, it's moles of product, gas phase, minus moles of reactant, gas phase. So in this situation, our delta N would be 2 minus 3, because there's 2 moles of gas there and 1 moles of gas there, that's 3. Delta N would be minus 1. So let's say this was at 25 degrees C and that Kc was 10. I'm just picking an easy number. It's not the real number, but we're just playing with this. Okay? So Kp here would be 10 times R, which is 0.0821. Remember, that's liters times atmospheres, moles, Kelvin. We're not super freaked out about units. The temperature needs to be in Kelvin, 298, and that's going to be raised to the minus 1. So Kp would be 10 times 0.0821 times 298 raised to the minus 1 power. And again, you guys can pop the numbers through. Okay? But if I'm given Kc, I can calculate Kp. If I was given Kp, I could calculate Kc. scroll up for me. Okay, that is the perfect place to end this lecture. The next lecture will start with types of equilibrium problems.